All right, new topic. We're talking about thermochemistry in the next chapter. Whoops, go back one. Apologies. And the idea is how do we understand chemical energy? And if you look at this bright yellow flower in a green field that might be familiar in this part of the country, some of you might know about this type of plant. It's called rapeseed. Also, a variety that's locally grown is called canola. And it has a lot of oil in it. It's used in variety of cooking purposes, but it also has applications in biodiesel fuels. All has to do with chemical energy. So what do we need to learn about in our first discussions here in this chapter? So we need to learn about the difference between heat and temperature, which seems a little bit like something you wouldn't have distinguished before. And what's the difference between potential and kinetic energy, and some of this other terminology, and some things about thermodynamics that we will get to gradually, some terminology. All right. If we know that you've heard someplace that we all should be conserving energy because there's an energy crisis in the planet, well, yeah. The energy is essentially, in its core definition, is the capacity to do work. Radiant energy comes from the sun, and it's the Earth's primary energy source, and without it we wouldn't have life the way we understand it. And there's thermal energy associated with the random motion of atoms and molecules. So motion equates to what amounts to heat in the molecules, thermal energy. There's chemical energy that's in the energy stored within bonds in chemical substances. So every chemical bond has an energy associated with it. There's also nuclear energy that's stored within the collection of neutrons and protons in the atom. And when you think about the fact that there's a bunch of protons in a very, very tiny space in the nucleus, there's a great potential for them to repel one another. So the fact that they do stay together in the nucleus makes one think there could be some energy potential by their positions, the way they're arranged there. And then another type is potential energy that we just describe as energy available by the virtue of an object's position. In other words, water at the top of the dam there has potential energy, and the energy is going to be usable if it goes over the dam or through the turbines to create energy in power plants by way of turning turbines and such. So the capacity to supply heat or do work is energy. Kinetic energy is the energy of motion. I hope some of you may have heard of that context. Motion and kinetic energy go together. You might see them with these designations of K after the symbol E. Or potential energy is stored energy, stored up in chemical bonds, and a lot of chemical compounds have a lot of stored energy, and we release them. For example, when we digest food, we release the energy so that you can build other molecules and move your muscles and breathe and do everything else that humans do. The law of conservation of energy tells us that energy can neither be created nor destroyed. You can only convert it from one form to another. And so the idea of the water at the top of a reservoir fits with this concept. And so at the top of the dam, at the top left there's potential energy. The water has potential energy. But as the water falls through the machinery of this generator at the dam, the powerhouse there, and it goes through the inlet, it goes through the turbines, it turns the turbines go to the air connected to the generator. So as the water falls through it, the velocity speeds up, increases, right? Potential energy is converted to kinetic energy to spin a turbine, and then you have electricity. And so we're converting between forms of energy. And so the total energy is the same, but we've converted some potential energy into kinetic energy, and then electricity it results. Aha. So conservation of energy, the total quantity of energy in the universe has got to be constant. So even if you have a burning methane flame here, and there's where's the energy going? You can analyze it with a visible laser and see what's happening with those particles. It's kind of a cool picture. Thermal energy and heat, we have to distinguish these a little bit. The kinetic energy of molecular motion is determined and measured by finding the temperature of an object. So temperature goes with kinetic energy, and that's thermal energy, has to do with heat, right? And heat is the amount of thermal energy transferred from one object to the other as a result of temperature difference between the two. It takes us a little while to think about these terms, and we'll be careful how we use them gradually. Okay, so you think of a thermometer, right? That's how you measure temperature. And so heat is transfer of thermal energy between two things that are at different temperature. So if you put your hand on the wall and the wall's colder, the hand transfers heat to the wall because it's going between the warm thing to the cold one. So temperature is a measure of thermal energy, again, how much kinetic or motion is there amongst the molecules and particles. But temperature is not the same as thermal energy. It kind of takes us a little bit to think about that. So thermal energy is that heat that's transferred between two things. So you think of a hot cup of beverage, whatever it is, your hot cup of cocoa or tea, whatever you like, compared to a big bathtub of water that's probably not quite so hot, so if you could take a bath without getting burned. And so what's the difference in the thermal energy of the two? The bathtub has greater thermal energy because it's partly related to the amount of mass in there. So the greater thermal energy results because you have more molecules at a greater energy that gives you a greater thermal energy there.